So as said, this video will talk about logarithm decrement. Okay, the first thing I'm gonna talk about is actually the relationship that we actually do last week. So what is this? We actually talk about the logarithm part. Okay, multiply by the sign, we eventually get a damping shape in this portion. So as you can see, the logarithm, the natural logarithm, actually affects how the sinusoidal would eventually become. So this is why the logarithm decrement concept comes in. Okay, the peak, the peak itself is, as you can see, if you don't look at the sinusoidal, it's actually actually con it's actually controlled by the amount of exponential decay in this case. Okay, controlled by some. I can't draw it properly, but you will understand that it's actually decaying exponentially, right? So this the amplitude of x1, okay, as we say earlier, this is x1. So please be careful. Okay, this whole thing is x1, and so this thing describes this just that they write it in here, so it may actually be kind of like misleading. Actually, no, sorry. Yeah. What am I talking? Okay, this give you the amplitude x1. Okay, so this is some amplitude, so which is x1 in this case. Okay, so the point x2 is like this point. Okay, this is x2, and then this one is x3 as what I have said earlier. So the relationship between x1 and x2 can be related by the logarithm curve. Okay, not with the sinusoidal. Okay, because the logarithm curve, as we see, affects how the sinusoidal turns out. Because sinusoidal keeps turning, keep going in the it oscillates and oscillates. It never stop decay down. Okay, so only the logarithm comes in, the sinusoidal will eventually decay. So with this understanding, let's go to the the first portion. So we can say that since x1 is related to x2, okay, since x1 is related to x2, gamma, okay, I think this is called gamma, okay, otherwise, yeah. So gamma or sigma, whatever, sorry, is equals to the natural log x1 divided by x2. So in other words, the natural logarithm x1 minus, because you are taking amplitude of this point minus this point, right? Taking this point minus this point. So from the logarithm rule, natural log x1 minus logarithm minus logarithm, you get division. Okay, so this is why it is this. So in other words, the purpose we use ln, okay, the purpose we use ln is because of this relationship. Since we know that the decay is in terms of logarithm, or otherwise exponential minus some value n, okay. So we don't care minus or plus, we just let it as saying that e to the power of n is equals to our amplitude x. In this case is our position. Okay. So therefore, in order to find how fast it decays, in order to find how fast it decay, typically you know that everything is due to this amount, this value n, right? The n is very important because negative is just saying it's going down. If it's positive, then it's exponentially going up. So the negative sign doesn't do much of a thing. Just about the n value. The value n is very important. So um this value will actually cause how fast it decay, or how slow it decay. So so that's why we want to find the value of n, which is in other words, next just now we actually talk about it. It is some values. Okay, the n, remember the damping factor. We are trying to find the damping factor. Okay, so in this case we need to find n, right? So since we know our amplitude already, we have to find n. So that's why we use the natural log base e x is equals to n. So if you forget this, it's okay. I just want to prove to you that why they actually use ln is because you want to find n. So in order to find n, you have to use ln base e of the amplitude in order to find the exponential of e. So I hope you get what I mean. So therefore, this is why they utilize ln x1. Okay, ln x1, which gives you how much n. So in other words, this is just saying en1, okay, and then minus en2 equals to some values. So this is how it. But nonetheless, it's being rewritten as this. Okay, I may be wrong over here, but the concept, it is this concept that why we actually use natural logarithm over here. So with this, and then you know that natural log x1 minus natural log x2 is just natural x1 divided by x2. This is the logarithm rules. If you forget, but nonetheless, let's go back. So with this concept, um, now knowing that the graph is actually oscillating, okay, then so you eventually decay until 0, but it is oscillating. From we'll know that it is under them because only under them has exhibit this trend, okay, exhibit that it is actually going down, oscillating. So if it's critical, then it's just like that. There's no oscillation. If it's over them, it will decay faster only. So there will be no oscillation. Only under them has oscillation. So this is why explain why we actually use the under them equation. And do take note that this is what we derived last week. And also that you need to know how to derive this. Okay, because apparently in this datasheet you are not given. Okay, you are only given this thing. Okay, I don't know, I forget what is this. If you remember, you can say so. But yeah, we are not given any of the under them or over them thing. If you are asked to derive that, then you have to really go and check it out. So you have a lot of things to actually learn and memorize. So as from last video, we actually talked about the final equation that we derive. Okay, this thing. So as I say, x1 divided by xn plus 1, the x is a function. So this x is actually our function, our underdamped function that we were actually saying all along, this one. So if you were to sub in x1, okay, let's say you say that you want to sub in x1, okay, because you want to find the values eventually, right? You want to find the values, um, because you want to find this value and this value, so you can solve for the damping factor, okay. So um, therefore, you have to sub in your t. Okay, in this case you have to sub in your t, and then the t is actually t1. Okay, t1 is not this point over here. T1 is actually we'll take at this point, half of the amplitude. Okay, half of the amplitude. But as you can see, it starts from here. If it's sine, it is cosine, then it does go. So apparently it's half of the amplitude. So we take t1 is here, t2, and t3. So therefore you can, in other words, t1 is actually 0 lah. Okay. So this is one key thing you need to make note. So when you do with this equation, you have to sub in all the t1s, and then you do with it. So you give me a while again. Since the underdamped equation is actually we rewrite into here. So the underdamped equation is this one, and then we want to solve for, saying we want to solve for the amount the n, which is e to the power of n, right? We want to solve for the exponential term. So therefore, one way is actually to solve, as I said earlier, is to use the x1 and xn plus 1. So in this case, I actually use x1 and x2 in this case. So therefore, this is x1 and this is x2. And nonetheless, please remember that this is the final equation we want to derive. So what we are doing now, eventually we'll derive this equation over here. I'm just trying to show you the meaning behind why we want to sub in all those things. Okay, so x1. So when you sub in 1, x1 is this position over here. right? So x1 will corresponds to t1, right? So it's t1 over here. So therefore, you just sub in the same equation. You'll get x1 and x2, okay, in terms of all these 1 and 2's. And then now there's a quick key understanding, okay. So there is two key understanding. One is that t1, the time at 1, is equals to t0 plus 1 period, okay. So in this case, we have no t0, so never mind, it's okay. But however, let's take a look at t2. So if t2 is equals to, so t2 is equals to t1 plus a period, right, from one cycle, from this from one peak to another peak. So it's one period itself. So this thing is actually a period. And if you remember, period is equals to 2 pi over omega. If it, if it's a natural system, it's natural frequency. If it's a damped system like this, we call it a damping frequency. Okay. So in other words, this is t1 plus 1 period. So 1 period is this one. Okay. So nonetheless, t3 is also t3 plus t2 and then another period. Okay. So this is how it is for the first understanding. So with this first understanding, we can actually use it in for the second understanding. So since you say only exponential affect the shape of the graph, okay, from the understanding that we actually talked about it previously, we say that exponential term will eventually cause a decay, right, of the sinusoidal. So therefore, we can assume that the sinusoidal is actually doesn't affect because as we say this. Okay, where am I? This points. Okay, this points are all part of the exponential curve. Okay, so this is why we actually assume that this portion over here is 0. Okay, or maybe perhaps 1, I would say. So in other words, so give me a while. So to prove, okay, because I'm just simply talking about it, right? So in order to prove, let me give you an thing. So sine omega t1 plus theta, which this represents what it represents. This represents this point over here. Okay, so t1 is actually this plus some theta. I mean, yeah, I mean some symbols lah. Okay, I forget what is it. And then while t2, okay, it's as you know t2 it's equals to t1 plus 1 period. Okay, so t2 over here is equals to t1 plus 1 period. So therefore, we can use this relationship. This one is our assumption. So we want to prove that in fact this is equals to this. So how do we prove? So therefore we use this equation first, and then we sub in t2, where t2 is from our previous understanding is t2 is equal to t1 plus 1 period, right? So this is where I write it down. So sine t2 is equals to sine t1 plus 1 period. 1 period is 2 pi over omega n. So therefore, if you sub t2 back into this equation, okay, I'm just subbing. So t2, okay, hold on. So t2, we just sub in over here. So I didn't change anything. Okay, I didn't change anything. So just sub in t2 over here, and then eventually when you multiply the omega n, okay, because there are bracket inside. So omega n t1 plus omega 2 pi. Okay, so this is so on again. So this will be so when you multiply omega in, you have omega t1 plus omega. Okay, sorry, this damn. This should be 2 pi. This should be 2 pi. Should be. Okay, so omega times omega is divided by omega. So this is 2 pi. Okay, so I believe you understand. And then you have this. So you know that 2 pi is just saying it is going in this thing. Okay, so it's just one period from here. So as you can see this point, so therefore we can say that 2 pi is just one period. So therefore we can say that we can eliminate 2 pi in this case, because there's nothing. 2 pi is simply saying that you go one round, and then let's say you start from here, you go one round, you come back here. This is the same thing back. So this is what it means. This is why I eliminate 2 pi, and therefore we have this thing. So what is this? This is the same as this. So we have successfully proved that we can assume that sine, this portion over here, is assumed that we are not using it, okay, because we are just using the exponential points, this points, the exponential points, to help us predict our thing. So with this understandings, next video I'll just we'll sub in this portion and this portion back into our x1 and x2. That means this thing over here. Okay, so next video we'll talk about it. And eventually we'll prove that will eventually come to here, and then we'll not eventually we'll eventually come to somewhere else in the middle. Okay, so this is what we talk about. So eventually we will derive until here, which x1 is equals to this portion over here, because we know sine. So and then after that later we'll talk about it. So yeah, I'll just see you in the next video.